Right, hi everyone. My name is Azriel, and thank you for coming to Rust Meetup. And today I will be presenting on why Rust. Convince me, is Rust just another programming language? Because that's the mentality I had before I learned Rust. And after using Rust for about 10, maybe 10, about 7 years, I certainly have learned many concepts in Rust that I do not see in other programming languages, and I hope that these will be made apparent to you in this talk. Our talk will be maybe just over an hour, so we'll try to get through all the concepts today. So here are our topics. We'll go through performance, constraints, expressiveness, unambiguity, tooling the ecosystem, and some benefits, some second order benefits. So the goodness that comes from the goodness. Our first topic, performance. No doubt, if you've heard about Rust, you would also have heard this phrase. Rust is blazingly fast. And this is always scattered on different Rust projects. My project is da-da-da project is blazingly fast and does da-da-da, right? So the term blazingly fast is claimed in so many Rust projects, but let's not look at the claims, let's look at the evidence. So let's look at some benchmarks. First being Lightning CSS. So Lightning CSS is a CSS minifier which takes a big CSS file, minifies it, and that's your small CSS file that you ship. The original CSS minifier, CSS Nano, took 544 milliseconds to compress or to minify a 10,000 line CSS file. And Lightning CSS takes 4. It's a little bit. And that's about 100 times speed up. So pretty evident that there is some benefits. If you are interested in web frameworks, the Tech Empower benchmarks, they measure the number of requests completed per second in different scenarios, such as reading from the database, reading with multiple queries, updating the database, so writes. And this covers the receiving of the request, the deserializing of your data, communication with the database, so some I/O, and then responding to the plans. So very realistic in terms of the measurements it's doing. And Rust does pretty well. So at least some of the Rust frameworks take up spots. And you do have other frameworks in other languages. So C, Java, JavaScript. So the language itself can matter, but the implementation also matters. And if you want to have some evidence for does the language have that much weighting over the performance, then you can look at the different benchmarks. So Rust, again, taking a lot of top spots, single query, multiple query. Rust does feature in the top end of those benchmarks. So there is some evidence to that claim. And in the benchmarks game, which primarily measures CPU efficiency and memory usage, C, C++, and Rust take top spots, and then you've got Julia, C#, Go, Java, Swift, and Node.js to feature as well. Now, there's a reason why these languages take the top spots, and we'll look at that quite shortly. So if we've established that Rust is fast, how is Rust fast? So let's look at compiled versus interpreted languages. For compiled languages, you take the source code, you run it through a compiler, and out comes the executable, which is your compiled logic. If you run the executable, when you run the executable, the only work done is the compiled logic, so very fast. For interpreted language, the executable that you ship is the source code. So what you're doing is, when you run the application, you're going to be parsing the source code, mapping variables to values, and then execute the logic. and we interleave this process between parsing and execution. And this overall interleaving means the overall execution is going to be slower. An analogy for this would be if I had a recipe given to me to bake a cake, but the recipe was given to me in a foreign language, I could take that recipe, translate it all into English, and then when I come to make the cake, I would do step 1, step 2, step 3, and essentially, if it's in my language, I can execute that recipe quite fast. But if I had the recipe in the foreign language and I didn't translate it, when I come to bake the cake, I'll have to go step 1, translate, do the step. Step 2, translate, do the step. And this translation process would mean the overall process would take longer. So that's the analogy for these two. And in more detail, how do you get CPU performance? Well, Rust to native CPU code. So first we'll look at this C, C++, Rust, Swift, Julia, a number of other languages. They have their compilers, which will compile the source code into something called LLVM IR, which is low-level virtual machine intermediate representation. And this is further compiled into the assembly for CPU-specific instructions. So there's Intel CPUs, which are like your Windows or Linux computers. There's ARM CPUs for your later Mac computers. And those instructions are specific to those CPUs. So they will run very fast. The caveat is you cannot run an Intel executable on ARM CPU or the other way around. You might be able to do some weird translation, but that's out of my league. Right. And side note, you can compile LLVM intermediate representation to WebAssembly, which runs in the browser. And this is an upcoming space. So, and this is how Rust gets CPU performance. It's going to run at native speeds on these CPUs. Another way that Rust gets runtime performance is how it uses memory. So memory in the computer is split into the stack and the heap. The stack is very fast. The heap is okay. But the reason why you need the heap is if you have arbitrary length strings, such as like your name, my name is six characters long. If someone else's name is shorter, then that arbitrary size string needs to live on the heap. Whereas because the stack needs to have fixed size variables. Now we're going to compare how Java and Rust use the memory. Oh, a question.
Sorry, I was just going to say, the other reason why the stack is limited is because it has a very limited size. Like the stack might only be like 2 megabytes or something. So very large objects need to be allocated up the heap. So.
Yeah, that too. If you try to allocate an array of size 10,000, your stack might overflow. And that's a different way of getting a stack overflow than recursively calling the same function. That's it. You do have this. So here's a little program where I put the value, it's number wrapped in an inner class. Actually, it's just big enough. So, okay, I'll make it one. So we've got a value wrapped in an inner class wrapped in an outer class, and we've got this main function. And in the main function, we'll have a string called hello, and we'll instantiate the outer inner value data. So there's the 3 levels there. In memory, what this looks like for the hello string, it lives in the heap, but there's an address reference from the stack. So that's the 7,000 hex here. And for the outer inner value hierarchy, you're going to have, well, we'll start from the stack. So 7008 is the address of the outer instance. 7000C is the address of the inner instance. And inner contains 1, 2, 3, the value. So there's a traversal needed to be done if you want to access the inner value. And so when you access output that value, you're going to traverse the stack heap, and this traversal takes time. and that's where you lose performance. So memory accesses. It may be nanoseconds, but nanoseconds times 100,000, right? That's going to start showing up in your user experience. Whereas the Rust version of this app, take your value, put it in the structs, in the object structs. Same logic, instantiate a string and instantiate outer inner value. In memory, we still have hello living on the feed and the address on the stack from the students. But for the object inner value hierarchy, you will see that the 1, 2, 3 lives directly on the stack. And this is what we call a zero cost abstraction. Abstraction being we've got the outer, inner, and value class or type abstraction. And in source code, you've got your classes, you've got your structs. But inside runtime, you have no concept of this hierarchy. All of that has been compiled away by when you run compiler. So the optimization means at runtime, there's zero cost to have had this abstraction. And so when you add 1 to 3, there's going to be no performance cost. So no performance cost, faster. Right. Now, before I move on to the next slide, I want you to imagine a programming language so garbage it needs garbage collector. Right. So ring memory. So when we use Rust, let's on the top right graph here, you will see that there's a purple line and there's a blue line. And the purple line is where we've got these spikes. And this is the average response time for some web requests. And every time there's a spike, that means the response took longer to be returned. And I want to explain garbage collection like this. Imagine I work with paper, and every time I'm done with paper, I put it on the table. And every 2 minutes, I'll look at what paper I've got, I go to the shredder, and I shred it. That's my deletion process of the paper. While I'm shredding the paper, I'm not doing work. And so if I'm not doing work, it's going to take longer for me to respond to her. And what this process of shredding paper is, freeing memory, is what garbage collection is. We have a separate process to free the memory that we have claimed, but we have not yet released. So what Rust is doing for not having garbage collection is we take the shredder, put it on the table, and every time I'm done with some paper, I shred it immediately. So there's no separate process to shred the paper, and so there's no separate there's no delay in incoming work. I immediately shred it. I keep processing my work file. So this is Rust not having garbage collection, and without garbage collection, you have a consistent performance profile. Your response times are going to be pretty much the same. This is a real graph from this code base image from Go to Rust for one of your services. Not
so let's go response times.
Correct. But it's quite small. It's still under 30 milliseconds. So Go is not slow. It's just they want to remove spikes. Yeah, the spikes. So if you read the blog post, they dug all the way down to try and make Go not. They try to tune the way Go does its garbage collection. So they did a lot of good work, but then they just could not get rid of this. Who are they? Discord. So in summary, for performance, so runtime performance depends on different factors such as CPU, memory, there are others like I/O and load, but CPU and memory are the main ones I look at. And LLVM-based languages compile to CPU-specific instructions, so they run very fast on the CPU. That's how you get fast performance. And for memory, it's split into the stack and the heap. stack is fast, heap is okay, and Rust makes use of the stack. So you don't always pay the heap cost. So by not paying that cost, you will gain performance. And if you do this, then the thousands of memory accesses will also benefit. And Rust has no garbage collection, so applications perform consistently, which is really nice for a web service.
Any substantial differences between Rust and C++ in this regard?
Safety. So
performance.
performance-wise,
I think C++ might lean on more undefined if it can, but Rust will be more conservative.
I think that benchmark game graph was useful, though I didn't say that. The language is pretty close, but C++ is still slightly.
yeah, it's you can get more performance because so if you heard of unsafe, that's where you tell the compiler, I don't need your help. And there's this thing where C++ is like having a giant unsafe block around all of your source code. So generally, the payoff for that is in performance. It's not worth the unsafety.
Case by case.
Case by case, yes. But you do make a call when you need to make a call. I'll move on to constraints. So even if Rust has no performance benefits at all, the rest of the talk is why I will still use Rust. Okay, so constraints. In the realm of software, there's all software. There's incorrect software, which is the red stuff, lots of those, and there's correct software, which is like little bit. Okay. So we want to spend our lives testing those correct software, not shipping the red software. Now, we'll go through what unconstrained source code versus constrained source code is. And unconstrained source code is where your source is executable. So you take your source and it's already runnable. And here's a little example. I call echo rara and it prints rara to my terminal. Whereas if I run rara on its own, it will run, it will fail. So this is unconstrained. I can run the program whatever I write to it. Whereas constrained source code is where I take my source and then run it through a compilation process, which I like to call constraint application. And if I pass those constraints, then I get an executable, then I can run something. If I did not pass compilation, I did not meet the constraints, then I don't have an executable, I have nothing to run. So here's a little Rust program. I assign 1 to A, I increment by 1, and I check it. And this will hit one of Rust constraints. It says I cannot assign twice to immutable variable A, which is text speak for, I can't uncheck it, I think. But I give.
Can't modify it.
Yeah. If I give a value to A, I can't change its value. That's immutable by default in Rust. And it says if I want to change a value, then I need to make it mutable. So I need to tell Rust this variable can change its value. And we'll do that right now. So now we've got mute A equals 1. So I've told Rust this variable can change its value. So this time when I run the program, I have satisfied Rust constraints, and it builds the program and it runs it. So easy, right? We're going to look at more or less versus more constraints. So for applications which are when you have applications which do not pass compilation, we're going to call them as invalid applications. And invalid applications we will call generally they are all incorrect, because if you cannot compile, then it's wrong. Whereas just because you have passed compilation, a valid program, it doesn't mean that your program is correct. So you can still valid incorrect programs. And those are the red bits inside the valid buckets. And our goal with constraints is to add more constraints so that the incorrect programs are considered invalid. So you cannot build a program until it's correct. That's our goal. Right? And so this is what Rust has done pretty well, but it does feel quite frustrating when you first encounter it. Question.
I guess one flavor for this graph is that even though a program doesn't pass Rust's compiler, it might actually be correct. It's just that I haven't convinced compiler enough. So
Yeah, there should be some
Wow, yes.
I'll give you the start of this pages. Or use JavaScript, right? Okay, so we're going to look at the nullability constraints of which JavaScript has none. Here's a little program. Here's a function which prints a string and it's length. And in JavaScript, this is incorrect usage, but it's considered valid. You can call print with nothing, and it will print undefined and an error. We can call print with undefined, which is a different kind of nothing. It'll print undefined and an error. You can call print with null, which is another kind of nothing. And you get null and an error. And the correct usage, at least in classes, you call print with a string, it will print hello and bye. So this is JavaScript. No constraints. It only works for the correct usage. You have no safeguards for the incorrect usage. Let's throw in a constraint. So C#, same function, takes a string, prints a string and its length. So we can call print with nothing. C# will not compile. If incorrect usage is considered invalid, you are safe. You can call print with null, which is nothing. It's incorrect usage. C# considers this to be valid, so you are not safe. You will hit an error at runtime, and I'll get to you in one moment. And you can call print with a string that's correct usage. It's valid and it works. So at least the correct grammar always works. The interesting bit is the middle one where we've got incorrect usage and it's considered valid. We want to make that safe.
It depends on your compiler. You may say that the second one is invalid.
Yeah. So I think
string is not nullable.
say that last bit again.
So string is not nullable here. It doesn't have a question mark.
Oh yeah. So I think later versions of C# you can encode the nullability straight into it. So yeah, the later versions of existing languages are adopting this semantic typing, which is really nice. Yeah. So if you're stuck with old versions of programming languages, sorry, but if you have a chance to upgrade your programming language or use Rust, you can have the safety. So here's how Rust deals with nullability. Same program, string and length. I call print with nothing. You will get a compilation error. And it's quite informative. Takes one argument, zero was supplied. We'll skip reading the messages for now. We can call print with none, which is Rust version of nothing. And Rust will say, you expected a string, but you gave me a maybe nothing. So this is also a violation of the nullability. So it's a completely different type. And if you call print with a string, then this will be the correct usage and it's considered valid. So what we've done here for line 7 is we've managed to translate that incorrect valid case into an incorrect invalid case. So that's how we gained a level of safety. And in Rust, if you want to accept nothing, then where we were accepting the string, we will now accept an option in the string. Completely different type. It's kind of like optional in Java. I don't know the C# version, but essentially the function definer will have to handle the case where the string is not there or the string is there. And so if it's not there, nothing. If it is there, it'll pick the string and it's like we can do this. And one thing you will find a bit weird is the first time you express what was the sum. So you can call print with none, which feels like just call print with null, right? And when you call print with a string, which is actually taken in as an option, you need to wrap the string with a sum and parentheses. Feels weird, you tend to get used to it after maybe a month, and it just feels quite natural after that. Question?
Would you say that there is no new reference by hero or undefined method hero, like it's doesn't exist in Rust at all?
There's no null reference or null pointer exception. You can have panics, which are when you have an option and you say, I believe it's going to be sum, and you never handle the none case. That's when your application can crash, but you have chosen that as a developer. Yeah, but otherwise, normally when you see an option, you would now know I need to handle it's there or it's not there. Yeah. Cool. Now here's another constraint, the other constraint. There's a data race in C# where we got the value, we increment it by 50,000 times. And we do that with 2 workers. So we've got the value, 2 different workers incrementing it by 50,000 times. Start them off, wait for them to finish, and return the value. If we run this, I will make that big. There we go. You will see that we get 90,000. And if I were to run this again, I get different values of 90,000. And if you're really lucky, you can get 100,000. And you so I have gotten 100,000 like twice. So yes, I spent some time just pressing up. But you can get 100,000. But the point actually is your program is running incorrect behavior, and C# has considered it valid. And normally, race conditions are not in one file. They're not called thread 0, thread 1. They are normally across like 20 files called service, like data 1 service or something other service. And you have to trace those threads from different web workers threads, right? So never as easy as this to figure out the race condition. Now let's run the same program in Rust. So this is the Rust version of the same program. Direct translation, data, value 0, increment by 1. So very fair. I spawn them, so I start with workers, I wait for them to finish, and I print the values. Now, if I were to run this, it doesn't let me. So it's red, and there's plenty of error messages here. We don't have to read them today. We just need to read this line. Aborting due to 5 previous errors. So we have hit at least 5 of Rust constraints. Who knows, we might hit 1 and then another constraint gets surfaced, right? So we have hit constraints which prevent us from compiling our program. We cannot run this until we have fixed those errors. And if I fix those errors very quickly, like that, we have wrapped our value inside a shared reference count and the lock. So essentially, if I want to access that value, I need to take all of it and make sure that no one else has access to it. So if I increment it, no one else can be reading that value as I have a lock on it. So we increment the value by 1,000 each, and the difference between the work function on that side and this side, before I can access the value, I must have acquired the lock to it. So if I were to start these workers and wait for them to finish, and then unwrap all of the locking mechanisms here, this weird syntax, if let, okay, really weird, but you'll get over that part. We'll see if this gets us the correct result. So 100,000, and to check we're not just lucky, we'll run this again. 100,000, and it's not just print 100,000. It's actually yeah. So we can improve that. That's our source code. So it's exactly the same source code that was run. All right. So we can see that Rust has protected us from actually compiling a program which has data risks. So we are safe when we have fixed the compilation errors, which are constraints which keep us safe. Then we can run our program. So no bad programs get shipped, at least if the race is within one process. Okay, so let's move on.
Did you force that to run?
Can I force that to run? Unsafe, and then a lot of unwraps. It will crash essentially. Yeah, and
what are the specific constraints which stop you from running, from creating a database?
so my mind is just shut up for now, but it's if you have shared access to a value, you need to have that shared access must either be immutable access, so multiple readers are fine, or one exclusive access, which is well, one writer. And the other way around, what we saw earlier on the previous slide, we can defer that shared access checking to runtime. So by default, Rust does exclusive access checks at compile time. But by wrapping it in the mutex and then R, which is atomic reference counts, to share that around, you have deferred the access checks to runtime. And mutex lets you have mutable access to a value as long as no one else has access to it. Which means when you see the lock calls, if 0 has the lock on the data, then work 1, when it calls lock, it has to wait for the data to be released, the lock to be released. And aside, when you call lock, you're actually holding onto a guard, which you don't have to remember to free that lock. Rust will automatically free that lock once it goes out of scope. Other languages, if you acquire a lock, you might need to remember to free it. Rust does it for you. So no performance essentially. Well, now Rust has over 9,000 error codes, lots of constraints. Alright, okay, not quite, not even 1,000, but I'd like to show people this one. 777. So what an error code is, everything is explained in this format. You've got what the error code means, so literal value of inside hash derived, and you've got a concrete example of the error, and you've got the explanation why it's an error, and you've got the recovery path. How do I fix my code to work? And it's not just documentation. If you never access documentation online, you just run your compiler or just save your file in IDE, you will get the same information in your console or in your IDE. So you don't have to go search Google or Stack Overflow for what's arbitrary code mean. It's going to be shown to you. Very easy, keeps you in the flow. And it's, if you think about lots of compilation errors, normally programming languages stop at the you're wrong stage, and then you have to go figure out how to make it right. And it doesn't tell you why you're wrong, it tells you you're wrong. Whereas Rust will go, you're wrong, but I think this is what you're trying to do, and this is how you can fix it, which is really user-friendly. And this is one of the things which it made me realize, I really value good usability. And so this is one of Rust's strong points as well.
How can I know that I need to use the new text? What's overlapping? When I see what's on the errors.
So some of the errors should show you in the help text. And if you, I'm not sure if this doesn't do this, let's fix this. It might be a bit too long to show in this presentation, but essentially the errors will guide you towards the right thing. And
They won't say explicitly that you need a new text here. They'll say things like this needs to have a set of lifetime and this way it can't be shared across threads, can't be accessed immediately across threads. It needs to be music. So it's kind of through experience that you would which things for some lectures, but some of that is all languages where it just says there was an error here and you have no idea why it is.
yeah, so at least you have some support on your own. So you might feel like I'm really good at programming, but I use Rust and I can't even do a basic program, right? And if you feel like I feel like a noob talking to my senior dev, there's none of that. You have to help yourself. You don't have to leave the computer. Right? So it's really nice to have that support before you need to reach out. Cool. Now, in summary, for constraints mark programs as invalid, and well-designed programs mark incorrect programs as invalid. So with strict constraints, more programs or more incorrect programs are marked as invalid, and so you get when you can compile, when you have a valid program, it's more likely to be correct. And this generally it makes the statement, if it compiles, it works to be more true than you're used to. So it's really nice to have that. And when you come to learning Rust, you will have a lot of times where you go, it's really hard to get Rust to get anything to compile, and you need to switch the mindset from doesn't work to actually the compiler is doing so much work for me. It's discovering and revealing all of the bugs that I would have had to fix, and I would have had to work to discover on my own, whereas it's just revealed for you before you can run your program. So maybe a deterrent for scripting, but maybe a very nice thing to have for a proper product. Cool. So one of the things I enjoy about this is it's expressive. So there's this thing called Coco mapping, which I like to call, so it's when you can map from your concept, something that you've designed, to code, and from code into something that you've designed. But not just can you map from concept to code or code to concept, but how easily can you map from code to concept? How much effort does it take? And first, we're going to experience this. On the left, you'll see this similar code. I'm going to read it out. You can even close your eyes. Helps. Let duration equals duration from seconds. 3 times 60 plus duration from seconds. 15 plus duration from seconds. 47 print duration as seconds. And we're going to read the code on the right. Let duration equals 3 minutes plus 15 seconds plus 47 seconds. Print duration. So much clearer. So much clearer. You can even do the math here. You probably like 180 plus 15, 195, 195 plus 47. 2.2, right? So you can run it. You'll see that we get the right values. But on the right, we know 3 minutes plus 15 seconds plus 47 seconds. When we format 2 seconds, it's so much easier to digest something that is clear. And this is what I like to highlight, because it's the clarity of reading code. Because code is written once and it's read maybe hundreds of times to understand how it works in order to change it, or it's read to figure out where a bug is. And reading code is takes a lot more. Well, because the operation is more frequent, the cost of writing is incurred once. You usually want to optimize for the high frequency operation. And even though code is written once, run hundreds of times, executed thousands of times, Rust with this, you're actually not losing performance by adding abstractions. So I will show you what backing code we have for both of these snippets. The snippet on the left is quite easy. It's just import the main function. So you're reading what it is. Whereas the code on the right, you're reading what it isn't. So we've got a trait, we've got an implementation for a trait, and we've got another trait in the implementation. So about 3 or 4 times more code than you're seeing. But the thing is, if we look into this, turning a number into duration, which is duration from seconds, same logic as the top. This is an abstraction because when you read the code on top, 3 minutes and 15 seconds, you're reading it at the conceptual level. You can understand it in your head. And just because at the code level, it's doing a bit more work translating it to integration. That additional source code, there's no runtime cost. This is another abstraction, which is zero cost at runtime. Compiler will optimize it away. So if you add abstractions to make it read better, sometimes you want to consider the cost of that abstraction. And at least for runtime performance, you can be sure that Rust has a lot of effort put into not adding runtime cost. Whereas in Java, if you add driver costs, it's more indirections. So that's the runtime cost. Cool. Now, here's a function. I'm returning a string from a function called fetch. Returns Azriel. I can call that function fetch and get a name. If I want to return 2 values, I can return a string, number, number in parentheses. And if I want to return that, the return statement is Azriel, 1, 2, 3 in parentheses, and the usage of that function is name, number parentheses, and I have those 2 as variables. Now, if you wanted to return multiple values in the language such as C# or Java, you don't have this thing called tuples, and so you'd have to create another class, which is a lot of boilerplate for expressing I want to return a string and a number. So the ability to express I want to return 2 things is very lightweight in terms of syntax in Rust. So if you want to say the concept in code, then Rust usually has a way of saying the concept. So you can express your concept in code quite easily. And yeah, question?
Yeah, so that function that exists to
Yeah.
what kind of use?
You can store there, or you can put that whole thing into a variable and call variable.0. It's indexed, 0 indexed tuples, and so you can ignore the second if you don't want it. Much easier. All right, so we're going to look at cloning. How do you express cloning in a language? So I want a deep copy or deep clone of some object in memory. And in many languages, I get quite sad when I see this. They tell you serialize your object, then deserialize it, and return that. And you see that C#, JavaScript, Ruby, and it's quite sad because what this code is telling you to do is, if I want to copy paste some text to another, so one tab, another tab, I want to copy from here to there. Instead of going Control-C, Control-V, or Command-V, you look at your first tab, you write up the text on paper, you take the paper to the second tab, you read your paper and go, oh, let's type it up. That is it. So don't, I don't understand this. But JavaScript has something nice recently called structured cloning, which lets do that. Yeah, so if you see serialization and deserialization as your method of deep cloning an object, it's very inefficient. And try to find an in-memory so a copy. How Rust does this is, remember how Rust is expressive? If I want my data type to be clone or copy, we'll get to the menu of that soon. We add this one line, hashtag derive clone comma copy. And that's it. You just go clone or copy, and it will make you a deep copy of the object. We'll see this in action and testing first.
What's the semantic difference between clone and copy?
Exactly what I'm going through. so copy. So here's a type, data type, called data, and it's got a value of a number. Now, if your data can be copied this bitwise, duplicated bitwise, we'll see in the picture shortly, then you want to derive clone and copy. So clone means I can duplicate myself. Copy means that clone is bitwise copyable. And we'll see this in this example. It's much clearer. So I'll instantiate a new object called data0. It's called data. It's a data type with 1, 2, 3 as its value. And on the stack, you will see 1, 2, 3 as its object, the blue lane. And if I go data1 equals data0, this will be a bitwise copy, meaning 1, 2, 3 on the stack becomes 1, 2, 3, a different instance on the stack, the purple one. And if I update data1 of value to 4, 5, 6, then you'll see that data0 has not changed. So we'll run this, and we'll see data0 being 1, 2, 3, and data1 being 4, 5, 6. That's it.
I should say it's not technically correct. Just that it's not a bitwise copy. It's that copy is the implicit version of clone. So clone has to be called explicitly. You have to explicitly say, I want to copy this object now by calling .clone. Copy basically says that every time this object gets moved, instead of moving it, copy it. So normally by default, Rust uses move semantics by default, whereas in C++, this comes from C++ basically, this is within C++. C++ uses copy by default, and so if you assign one object to another in C++, by default it will copy it to the other object. Even if that's a deep clone, it's quite expensive. In Rust, basically everything is moved by default, so if you assign one object to another, it will move that object, so it's quite expensive to clone it. It won't clone it, it'll just move all the pointers and stuff over to the new object. So if you implement copy, then it basically says, okay, if I assign this to something, I want you to do a deep copy, like I want you to copy it rather than move it. Like by default. Just changes the implicit behavior. It's what copy trick is. It was fun. So.
I'm telling you guys lies. But I believe this lies. Oh, actually,
One thing this kind of bothered me in this one is that, like, it makes total sense. But it means that if I add a clone annotation to my struct, then like somewhere on the rest of the code base, behavior can change. Like imagine, like I have this data0, data1 line, like somewhere else in the code base, and now someone added like a clone annotation to data, and now my code changed with just this very scary action at a distance to me.
It doesn't. Clone doesn't change the behavior of your code. But copy will.
Yes, but if I were to delete copy from this code base, then the output will change in 4, 5, 6, 4, 5, 6.
If you change,
if
you delete copy, if you didn't,
That will be a
the
move.
second will be a move. So basically, at that point, data0 becomes invalid.
Yeah, so once if you take a copy, then data0 is now inside data1. You have no more data0. You call data0 value and get compilation error.
Also, like that doesn't compile.
Yeah.
Okay, that's
Part of Rust safety.
What if it was the other way? What if you had moved? I'm guessing move is quite restricted.
So the other way around, the danger is that if you make a copy of something that was previously moved, you'll get a lot of implicit copies, which if the copy is expensive, then it can be a performance thing. So
We'll change the semantics.
only if you mess up the implementation of move one of the the copy of one of the underlying objects. So if you have a custom object and you implement copy, because you don't have to derive it the way that these traits work to derive will automatically derive the implementation of the trait if all the members of that struct implement the trait. So it's easy for things like U32 to implement things like move and copy. If you had your own struct which acted a raw pointer, for instance, then you have to implement copy manually. You can't just derive it. But you can derive it and say, I want to copy the pointer, but that's like an unsafe thing. You have to explicitly say, I want.
I think the question maybe is when you implement copy for a struct, what would happen if you made an assignment like this, but you haven't used it after that? So in theory, it can be moved, right?
Or I guess just basically say I had a semester program using Moodle. If I went into the struct and derived copy for it, apart from the digital performance cost, can it make the program
No, no.
because you kind of have used
because you have widened the constraint. But I think
we should move on. we just content, so we gotta count time. So clone, you might correct it as well, but say we have some data on the heap. So we've got a string on the heap, and in this case I've also got the number. And if we instantiate data 0 being the number and the value on the heap, then we'll have that new hello string. We've got the reference to it inside our stack objects, and our stack object also contains the number. And if we were to clone it, which is an explicit call, then what we get is the purple object, and we've got 1, 2, 3, which is the bitwise call. Right. And we got 7,000. Okay. We got copy, and then we got 7,008, which is the address of the cloned string, and it's uppercase has to be uppercase, and so the addresses are obviously different for hello and hello, right? So the hello needs to be referenced by the second object, not the first, and the second object doesn't want to reference this one. And that's why you get different values of the stack. And if we were to print this, it should be 1, 2, 3 is copied, and the hello is cloned and made up the case of the second.
This is a great example of the semantic difference because string doesn't implement copy, it only implements clone, and so you have to explicitly copy it. And that's because it's expensive to copy a string that's allocated on heap because it's creating a new heap allocation for that second copy.
So in summary for expressiveness, expressiveness is a measure of how easy it is to express a concept in code and how easy it is to read the code and then grasp the concept. And Rust has constructs to make this easy. So if you can think it, then hopefully there's very little syntax to express that thought. And when the code is read, well, less syntax means easier to digest. You should be able to understand what it is doing. Cool. Now, paired with expressiveness is unambiguity. So where expressiveness is how easy it is to say what you want, unambiguity is how easy it is to look at what you want, or look at what is said and infer the meaning of what is said. If there's any guesswork, then that is ambiguous, and we don't like that. So we've got this question. Who's not a dev here? No, who's not a developer? No. Right, okay. I'll pick Colin. Are these the same?
I'm going to say no because I studied same is a defined verb.
So exactly the confusion we have with ambiguity, because for developers, engineers, we know that the same or the word equal has multiple meanings. We have to guess which is the meaning that I'm asking, right? That's ambiguous. That causes confusion. Now, equality in Java, very really quickly, line 11, does ABC equal ABC? It's true. So yes, we'll get to, well, I won't explain it, but we'll just do the same. All right, so does ABC equal AB plus C? True. Does ABC equal AB plus C if they're in variables? False. What do you say? Does 1, 2, 3 equal 1, 2, 3? True. No trick questions yet. Does new data 1, 2, 3 equal new data 1, 2, 3?
Boxing is the
Yeah. So in Java, sometimes equals, the equals operator means value equality. Sometimes it means referential equality, which is, so these are both the same value, but code can 1, code can 2, referential equality difference. Right, so that's the difference, and we are off ball. I get tripped by this all the time. And so I really don't like ambiguity. So that's why I chose first. So here's the same comparisons. This time, if we were to run the code, we will hit, because in Rust, if you have a type, if you haven't told Rust this type can be compared with the equals operator, then Rust will refuse to do that, because the equals operation cannot be applied to type data. So it tells you where it is, right? And so earlier we saw Rust very helpful with it. Error messages, it tells you try adding hashtag direct partial equal to data. So if we do this, and so we add this to that, what we get is the same code with that. When you run the program, what we get for the comparisons is they're all equal, because equality is done all by value. No confusion, no accidentally wrapping a type in another type. Suddenly the semantics change. So no ambiguity in that. And if you wanted to have referential equality, which I find quite rare, then you can call standard pointer equal data 0, data 1. And so in this snippet, we've got data which has a string, and data 1, which is data 0 clone. So we made a duplicate of it. They have the same value equality, but they have different referential equality. And if we hit the OK button to pass those assertions. Right. Okay, so one more thing with ambiguity or unambiguity. So let's look at control flow, which is often can be ambiguous. So here's a context. My download method has 2 good outcomes and 3 erroneous outcomes. We downloaded the file, we previously downloaded the file, and we don't have to this time. And we couldn't connect to the server to download the file, or we connected but halfway through our download. We got lost, we lost our connection, or the server was attacked server and ran out of disk space. I've never done that. All right, so here's control flow in Java. So the download method, we can symbolize the successful return to the enum of success downloaded page and 3 exceptions. So these conceptually map very easily to this concept. You can see the code, you can map the concepts. Now that's not where the ambiguity is. It's in its usage. Often in Java or any other language which gives us try blocks, we're tempted to write things like this: try, download, upload, or try and do a number of good stuff. And if there's any bad stuff, then here's our catch statements to catch those errors. Now the problem with this is the unknown host exception. If I work with this exception handler, I cannot tell unambiguously without any trace of doubt, right? That's I came from the first download, second download, or the upload. I could have come from any of them. So this is ambiguity. And the concept that we have implemented is this. So unknown host it can come from any of these three paths, and I can at most get compile time. At runtime, you might have the line number of this thing, and you might have the string for the path that you're downloading or the URL that you're downloading. But at compile time, I cannot unambiguously guess. Whereas if we want to be unambiguous in Java, we have to write this code. So try first download, and it's exception handler. Try second download, it's exception handler, and try those. And with this code structure, if I have an unknown post exception on line 4, undeniable, I came from line 2. If I have a unknown post exception on line 11, undeniable, I came from line 9. There's no possibility I came from line 2 because that's the only thing that can be tried on, right? And same for upload, if I hit one of these, it definitely came from line 16. And the concepts that we have implemented is this. So we've got an individual exception handler per exception case, but it comes from only one line of code. And to code this, I had to think. I had to deliberately code in this style. Whereas Java, when you learn Java, you are taught, oh, try, do your stuff, and then bad stuff is on the catches. So we are taught naturally to use the first form, and that's not the form. Can we reach the second form, the unambiguity, without having to spend effort? Right? So this is what I like to show you with REST. So in REST, we've got the same download method. It's written a little bit differently. Our return type is a result with success, which is an enum or downloaded and cached. Same structure as Java, but our failure cases, instead of encoded in exceptions, we have another enum called fail. You can name it what you want, and you have the failure cases, and these can be these are put into the fail enum, which is the second type parameter for the result enum. You'll get used to result as you use Rust, but essentially result is if my function can fail, then use a result as the return type, the general recommendation. So we've encoded the same concept into the download function signature. And on the usage side, when you call download, the return type is going to be the result, which means you have to handle all possible outcomes of that download function at the same level of importance. So whether it's successful or a failure, you'll see them all in the same log. So you don't have this accidental, let's call download 1 and download 2, and accidentally group the exception handlers or the failure cases together. So what this means is, when you call download 1, so you call download second time, you're going to automatically write failure cases or failure handlers per result. So this is the natural way of writing Rust code. There's no try, so you can't accidentally write the root variants. And because Rust guides you to writing this style, you have automatically been guided to write the unambiguous form of code. So you're going to have good code by design. Yeah. So doing the right thing is the easy thing. Yeah. And if you forget to handle a fallable method, what you will get from the Rust compiler is a compile error. So a fallable method will produce a message called unused result that must be used, and Rust will point to the line of code where you haven't handled a possible failing method, somewhere that your program could fail. And if you really didn't want to handle it, Rust tells you you can add this as well. Let's underscore equals then the possible failing method. Then that way you can tell Rust, I don't want to handle this failure case, it's all right. So this in this way, Rust has led us to write unambiguous code, and you're just never going to run into a case where I'm reading code and I don't know where the calling code came from. So in summary, ambiguity happens when there are multiple meanings, and you have to guess for what is said, which is the right one. Expressiveness lets you say what you want, and unambiguity means based on what is said, you can undeniably map to what's wanted. And Rust guides you to writing unambiguous code, meaning lower maintenance costs when coming to investigate issues. Nearly more than so tooling. So Rust ships with a lot of standard tooling. The first is called Rust format. It's a very original name. It takes your code, formats it, and does this. So you feed it a thing on the left, it's this thing out. Standard. You don't have to choose between different formatting tools. This is the one. And you can configure it, but generally the defaults are quite good. Rust ships with a lint of Pippies, also very original name. If you write the code on the left, Pippy will say, warning, you seem to be writing da da da. And when Pippy tells you, I want you to write something else, essentially it's telling you, I see what you're doing, but this is the idiomatic way of writing it in Rust. So if you want to write clean code, then the Pippy lets generally tell you a way to write it. And that way tends to be less confusing or essentially a better way to express the concept that you want. And there are many, many links from Pippy. It's got over 9,000. So, right, so plenty. If you spend your time reading the Pippy links, then you will learn a lot about Rust. But if you wanted to tell Pippy, actually, this time let me write this code, then you can add hashtag allow Pippy single match. The single match changes based on the length that the file is. So you can tell Pippy, let me do this once. Rust shipped with a package manager. So we have one, it's called cargo. So some people know why one is. Anyway, all the standard commands are there. So you can initialize the project, build it, run it, test it, publish it. If you change your source code and you just run, it will build and run for you. I expected that with some tools, but some actually need you to run build first. But no surprise. Anyway, our package descriptor is quite short. Name, version, edition for the later newer side, and dependencies. Dependency name equals version. There's this thing called features, which lets you turn on additional features for your dependencies, and this aids with compilation. As in, if you have features that you don't use, you don't have to spend the time compiling that. So generally, you can turn things off if you don't need them. Your project will compile faster. And we have comments in the package descriptor, which is it's just nice to know why this dependency is there. There are many other tools by the community. Cargo audit will tell you if any of the dependencies and transitive dependencies contains a security vulnerability, and then you might want to upgrade. Cargo deny tells you, well, you can tell cargo deny, my project is only compatible with these licenses. So if you have any dependencies which have licenses that you are not compatible with, then cargo deny will tell you that. And you can fail the build on having a dependency which is incompatible. Cargo about collates all the licenses from your dependencies and puts them into a web page so you can publish. My product uses all of these dependencies. Here are the licenses for them, and that helps you be compliant with the license terms. And all of these, before that, more subcommands are in the RS hashtag cargo subcommand dependency, and all of these are integratable into your build pipeline. So I've done this for my some of my projects, audits, license, format, docs, and style check, the coverage, etc. So all the standard quality checks can be automated, and so you don't have to wonder which tool to use. In general, there's always one blessed tool to use. Cool. In summary, Rust ships with standard tooling, and generally everyone uses the same tooling. So when you download someone else's project, you know the commands to run because it's not custom. And so with these standardization, you can focus on development and not on the flavor of the day. Cool. Rust ecosystem. There's a variety of, just check time. We're good to stay 15 minutes. So there's a variety of software domains that Rust has been used to build apps in. So there's command line applications. That is a cat clone. So cat will print the contents of a file. That will print the same contents of a file with color. Grep is the grep clone, but much faster and has nice defaults like git ignore files. New shell is a shell written in Rust. It's a new shell. Yeah, the creator of new shell, Jonathan Turner, and I remember the other two. They presented new shell in the Rust Meetup before COVID. Native applications. So this terminal I'm using is called Warp, and it works on Linux now. I'm very happy. And Warp's really nice because with terminal applications, normally you run your command, and you're like, I can't find the command because the command has gone up, like up the screen. And now it's like sticky on top there, so you know that this is the command I'm running. This is its output. I can press up, and you can see this is the previous command I run. This is its output, and I can go between commands just by pressing up and down. It's really, really nice. It's a dev thing. Z is a text editor, probably going to be quite big. Web development, so you can compile Rust to WebAssembly. Some of the diagrams in this presentation were done by something called .ix. That's my little side project. Lactose and Diopsis are the reactive frameworks, which similar to React, but written in Rust and compiled to WebAssembly. They are really interesting to watch because they are both very high performance. And game development, Bevy is a flagship game engine built in Rust. It's got support for 2D rendering, 3D rendering. So if you're into game dev, you do have support. And I watched this for like 10 seconds. I did this like that. I built this 5 years ago. So that's enough. Yeah, but that was built in Rust, and it could compile to both a native app and WebAssembly at the same time. So you can single source your game and have it compile to different target architectures. And for embedded systems, you can compile Rust and target embedded systems like Arduino, Raspberry Pi, Risky, yeah. Yeah, so if you're interested in that, then look at Pro.rs. It's got good docs, good tooling.
Is Firefox written in Rust or Firefox?
I don't think so. I think parts of Firefox might be using Rust components, like the renderer. Yeah. We had a Firefox person before, so they would be able to understand. All right. So with the ecosystem, it's just quite stable. As in, you build something in Rust 1.02, it will build in Rust 1.78. I have experienced that. I built a log parser in my first workplace, and then many years later, when I left, I upgraded Rust, upgraded my dependencies. It worked, just worked, right? So it's quite rare to find software libraries or frameworks where you upgrade all the things and run it, and it just works, you have that guarantee with Rust. The community, I think this is not just a like software semantic versioning thing. It's also the community mindset. Many people in the community, they don't want to claim my software version 1.0 because they know maybe there's one chance where the API will change. So generally, people are quite conscious about keeping the upgrade path smooth. Question. Yeah.
Do you so fast?
Yes.
You have support for like gateway.
I don't know.
Probo is just it's a tool for like interfacing to microcontrollers and stuff to interface into hardware. It's not really it's not a library or like ecosystem, but there are ecosystems within Rust for doing things like IoT gateways for like A2 when you put in like and what's the Sigfox and Zigbee and all those things like there's Rust libraries that exist for those things if you're looking to try and use it for IoT. It depends on the specific protocol and the Rust embedded stack using things like that. But that's very good support to it. If you want to really want to do something in Rust, it's probably a stack instead of driver that you can use to kind of string something together. Not Probe, but like other stuff within the ecosystem. Probe is just one tool within Rust embedded ecosystem. I think, we're just using it as an example of like one tool in the entire ecosystem of tools related to Rust.
So we know Rust is used in a variety of contexts. Rust is stable, and we'll look at some of the second-order benefits of Rust. This is the last section. So there's a cleanup event when we use Rust. You know that we get more constraints, so there are fewer bugs. When you have fewer bugs, you should have happier customers. When you have happier customers, you get actual profits. And when you have actual profits, you have no layoffs. This is my grandson. Yeah, but I can guarantee the first two, not the last three. Right. Okay. So
What is precision? This name.
Yeah, in summary, so Rust gives us performance through good CPU efficiency and memory usage. Constraints help us build correct programs and prevent us from building incorrect programs. The expressiveness and unambiguity mean you can express what you want, what you think, and you can unambiguously figure out what's meant by the code that you see, what it says. And tooling. The tooling is you have the tooling built in, so you don't have to focus on what's the best tool to use because the best tool is the only tool, and so you can keep in the flow of development without worrying about the other parts of the development process. Ecosystem stable, and you get all of these benefits by actually trying Rust. So it is nice to hear about the benefits, but you will only conceptually know this. But when you try this, then you intrinsically know it. And there is a big learning curve. But after you have learned Rust, it's really hard to go back. So I'd like to say thank you for listening, and I'd like to open the floor for questions.
Is there anything that annoys you about Rust that you wish it would do different?
So anything that annoys me about Rust, the never type is named after its stabilization date.
The what type?
The never type. So essentially, when a followable function, when there's an interface which supposedly can be followable, but you know that your implementation cannot fail, you should be able to tell Rust, hey, it's never going to fail, and you can't do that right now. Yeah. I guess another thing.
This is infallible.
there's an infallible, but there's no smooth upgrade path right now.
Right.
That's why they didn't stabilize it. I guess the more realistic answer is some of the async error messages are quite difficult to understand. So there's a whole other section of Rust called async Rust, and when you have an error in async Rust or compilation error, it's usually to do with a static lifetime, and you can't tell which variable inside my block of logic needs that static lifetime. I haven't explained lifetimes. So that's one of the hardest things to diagnose.
So I don't use Rust, but I know about like large, for example, so that that's just curious for because you guys also have used it for a while. Does it become intuitive at a certain stage, or is it, or do you still sort of act like backward?
So I would say it would become intuitive, and when I write Java now, I expect a compilation error, which I don't have. And so essentially I'm writing Rust in Java syntax, and I expect the compilation error, and I don't get it. So I don't get the free informative that I've made a mistake here, which I've deliberately left for my future self to fix, but I don't get that. I don't get that error for me. Yeah, and so it does become quite intuitive. So you miss the compilation errors.
Does it have generics?
It does. So results we saw earlier with the success fail. That's generic.
Do you often get with the effective group just today, like, you I think the rest
Yes, plenty of times. So I only do this with Rust projects where I would change the interface of a widely used, it's called traits. It's like interfaces in other languages. When I have changed that interface, pretty much the whole code base turns into, like, say, 100 plus compilation errors, not exaggerating. And I like that because I can change something fundamental and resolve those compilation errors, and everything would just work. I have done this. Like, you can see a like 70K line of code change, and all my tests just pass when I fix the compilation errors. And I don't have that level of confidence with any less constrained programming language.
Yeah, in production, we don't use Rust. In production, we have lots of tests, unit tests, integration, all kinds of tests. And I'm pretty sure that in Rust programs, they write on the tests. But the existence of test means something can go wrong at one time, and that's what tests are for.
Yeah.
Those are for capturing the long time wrong behaviors. So there are actually two kinds of wrong behaviors. One is compile time check. The other is runtime errors. And I think the question is where we should draw the line about which behavior you should capture at compile time, which type of errors you only capture at runtime. I saw somebody use TypeScript to do actual computation because TypeScript's type system is Turing complete. So technically, you can capture every bug in compile time, but that's too exaggerated, and that's not an efficient way to do things. So my question is, do you think sometimes the line Rust is drawn between compile time and runtime errors is a little bit too strict, and maybe some errors can be captured more efficiently by just writing tests?
So sometimes the errors that you get at compile time are encoded into how you've written your code. So for example, a builder which requires, say, you need to set field 1, field 2, field 3, and then call build, and the build method is followable. You can encode that into a compile time error where if you haven't set field 1, 2, or 3, any of them, then the build method doesn't get exposed to you. So that's a compile time error that you can choose either runtime or compile time, and both have its costs. sometimes you want to have the runtime error because it's easier to write the code for that. So you can choose is the short answer. And being able to choose is always good because we know the cost of doing either one or the other. If you're forced to do one or forced to do the other, then well, you can't balance the cost of development. Whereas if you do need to save time and get something working at the cost of the compile time error, then at least you have the choice. Yeah.
I think the community because it's like pushing something towards the power line if possible. The Rust libraries that is an example of diesel with SQL or for Rust like that's for a lot of errors into the power line, but it also is extremely slow to compile. And it's quite complicated sometimes, so it's a different process. You need physical limitations.
Yeah, how long do you wait for the pilot and do you buy like a custom laptop?
I did buy a faster laptop for that
You
reason.
were just talking about that before.
Yeah, I actually was trying to buy a laptop. Anyway, so most of the time I don't have to wait for compilation because there is a shorter version called check, which gives you most of the errors anyway, and so that happens within a second with the faster computer. And the actual compilation, I do wait for that, but not actively. I don't watch it. Well, say on GitHub Actions, I just push, and I don't have to worry about it because usually after you've gotten your checks working and run a unit test. So running unit tests requires compilation, 100K line of code repository. I generally just wait for a few minutes because there's incremental compilation as well. And the way you structure your code really matters. So I've separated all my unit tests out into one project so that the only time I need to incur the cost of linking, which is the most expensive part of compilation, is once. So I got 1,000 tests in one project instead of, say, 100 little crates with 10 tests each. So the linking cost is quite high. Switch your faster linker, and you still want to only pay that once.
Most of the compilation cost is actually compiling the dependencies.
Speaking of dependencies, how big is that standard library? How much you can do without bringing other dependencies or other parts?
So there is a, what do you call it? When you do link time optimization, I think it strips all of the unnecessary code, native code from your binary, so you don't carry that in the executable.
Okay, I will rephrase. Can you use network files, but whatever, without any dependencies?
The standard library includes everything you normally need, like IO and things. It's kind of split up into layers as well. I talked about this in my embedded talk last time. But the library is split up into like core functionality, which is not platform dependent. And then there's like a big layer of platform dependent stuff that sits on top and uses all this functionality like IO and memory management, dynamic allocation, network stuff and things like that. So, but usually it's very low level network stuff. So I think much network stuff is implemented in standard library. I think it's just sockets and raw sockets and things like that. And then to get anything higher like HTTP and then you need to bring out other dependencies. Like high stuff.
HTTP over dependencies.
Yeah.
I think so.
They try to keep the standard library small.
Okay.
Yeah. And question for that.
Yeah, for someone new to Rust, what would be your advice to folks? Do you think borrowers and takers need to focus on standard? This is something.
Yes. So if you follow the Rust book, rust9.org/book, I think they've got a nice sequence of topics to go through with examples, small snippets, so you can understand each concept individually. And that's what I would recommend, because that's what I went through and I understood it. And you can try to write some small programs, Like just write some command line app, because at that level, just understanding a reference, like are you passing a value or are you passing a reference, and understanding the barrel checker and lifetimes, that takes quite a bit of time. Yeah.
So there is a book, Learn C++ for 24 hours. How much time do you need to learn Rust?
So I thought I was confident at 1 month, then I thought I was confident at 3 months, then I thought I was confident at 6 months, and I think I'm generally confident on that.
Dunning-Kruger curve.
So 6 months.
That's when I would be quite confident, yeah.
Until you learn async.
Another thing, took me another year, but when you have gotten comfortable with async, then I don't think you get comfortable with async.
There is also so secure C++, which has more than 1,000 pages. I think it's just part of us.
So it's like a 700 pages book for C++ templates.
You can't learn all C++.
What I'm going to do with my web free time.
Taking that architecture, how to get the compiler to actually compile your program. Because now, instead of compiling your incorrect program, one compile your correct program. Instead of thinking about how to compile your correct program by making it correct in the form that the compiler can understand.
Now, with it, is that frustrating? Because obviously one part, also another part that I literally don't care about the because I don't care about what's not
You can call the unwrap, which is the version of let it crash if it doesn't work. I think I have this somewhere.
But still, borrow checker can be really annoying.
Yeah, it doesn't reduce the constraints. It just allows you to bypass some of the boilerplate dealing with that sort of thing. But
personally, I found the C++ very good for prototyping, and the Rust very good for production.
yeah, I think you can prototype in Rust only after you've already learned the language. You have to internalize. This kind of goes back to your question before. Like you have to internalize all the compiler rules and things first, so that you can kind of write good code the first time, rather than having to like bang your head against the borrow checker. Eventually, you get to the point where you know what the borrow checker is going to tell you, and so when you design things, you kind of design them in a way which is like, well, I have to avoid this thing because I know the compiler will understand that. I can't design like this because I'll have one with this constraint or things like that. So you kind of internalize the constraints.
I'm going to take one question in that closer. People can read.
So you mentioned about like web application. What are the web applications that we develop using Rust? Like what kind of like famous e-commerce or
I don't know about famous, but
it's not famous, but you know what I mean.
Just for one. Just for business products. These are both on the front end and the back end, right?
don't know. But
say for example, like a small CMS web application built in Rust.
Web applications.
Can you? It's not going to. Okay. So this is written in Rust itself, and if I change some text in my code on the left, you can see the diagrams regenerated. If I change the edges, so I take this one away, it changes where the arrows point. So this is just one example of something you can write in Rust.
I think at the moment mostly Rust inside a web domain would be if we have some Rust algorithms or some Rust libraries that we want to reuse in the web application. We want to compile it to code in JavaScript. But like a full-blown like DOM manipulation library, it's still
Well, thank you for everyone for your questions. If you want to ask more, we can go on after we close. All right. So thank you for listening, and